For years, the machine learning industry operated on a strict division of labor. Research meant PyTorch, production meant TensorFlow. In that ecosystem, Keras was widely viewed as a beginner-friendly frontend, the training wheels built directly into the TensorFlow 2.0 architecture to help newcomers define simple layers. With the release of Keras 3, the development team dismantled that architecture. The framework has entirely abandoned its TensorFlow exclusivity. Keras is now a cross-framework translation layer. It sits structurally above the three major execution engines, TensorFlow, PyTorch, and Google's JAX. While native PyTorch commands over 70% of academic preprints, Keras dominates applied physics and enterprise production. It operates as the infrastructural backbone for Waymo's autonomous driving models and processes petabytes of particle collision data at CERN. By decoupling the semantic definition of a neural network from its execution engine, organizations neutralize cloud hardware lock-in. But achieving this hardware neutrality requires accepting specific, unavoidable engineering trade-offs in how state is managed and how errors are debugged. Keras mitigates the cognitive overload of machine learning by standardizing the developer experience. It heavily borrows from the scikit-learn estimator model, reducing the lifecycle of a model to 3 intuitive verbs: compile, fit, and predict. Rather than forcing an engineer to manually manage a chaotic mathematical graph, Keras treats neural networks as isolated, interchangeable objects. Each layer inherently encapsulates its own state and forward-pass multivariable calculus. This modularity relies on the progressive disclosure of complexity. Developers access deeper levels of architectural control incrementally. At the first level, the sequential API allows data scientists to build simple, linear stacks of layers. Each layer accepts one input tensor and yields one output. If an architecture requires multiple inputs, shared layers, or residual connections, developers move to the second level, the functional API. This accommodates nonlinear data flows by routing tensors through a directed acyclic graph. For total object-oriented control, the third level allows researchers to subclass the base model object. Here, they can manually override the train step method to dictate the exact logic of a forward toss. This continuum ensures that as an engineering team scales the complexity of their models, they never have to unlearn their foundational API tools or rewrite their existing codebases. Executing a single Python script across different frameworks presents a direct structural contradiction. PyTorch uses an imperative execution model. TensorFlow relies on static graphs. JAX demands strict functional purity. The mechanism resolving these conflicting requirements is the keras.ops namespace. This module provides a single, unified implementation of standard NumPy-style tensor operations. When a developer writes a high-level mathematical declaration in their script, the system intercepts the call. A dynamic router checks a specific environment variable to determine the active backend. The operation is instantly resolved and pushed down to the highly specialized C++ or CUDA kernels of that specific engine, executing natively as jax.numpy.matrix, torch.matrix, or tf.lineal.matrix. This interception layer extends directly to data ingestion. A team can natively run a PyTorch data loader through a Keras model without throwing a type error. Likewise, they can feed highly scalable tf.data.dataset pipelines into the exact same model, regardless of whether the execution backend is PyTorch or JAX. Disparate enterprise teams can now share their exact data loading methodologies instantly, completely bypassing the underlying execution framework. The keras.ops boundary cuts machine learning operations overhead by eliminating the need to rewrite complex extract, transform, and load pipelines every time hardware constraints force a switch in execution engines. Integrating JAX into this system was the highest technical hurdle for the Keras team due to a sharp conflict regarding state management. JAX enforces a strict functional purity constraint. It explicitly forbids hidden side effects, meaning a function cannot alter any internal state or variable during computation. This directly conflicts with how PyTorch operates. In PyTorch, computational nodes dynamically update their internal weight matrices natively inside the computational graph as the process runs. Typically, the mathematical weights of the neural network are no longer stored inside the computational operations. They are managed entirely on the outside. During a training step, Keras explicitly passes the current external weight state alongside the input data batch into the compiled training function. The backend engine computes the forward pass, calculates the gradients via automatic differentiation, and explicitly returns those gradient vectors to an external optimizer, which then updates the state. By forcing all operations into a strictly stateless architecture, Keras achieved exact mathematical parity across 3 incompatible deep learning philosophies. This chart compares training throughput on a large language model across different backends. By integrating JAX, Keras unlocks aggressive accelerated linear algebra compiler fusions that drastically reduce GPU memory read and write latency, yielding speedups of 20 to 350% over standard baselines. However, this performance comes with an engineering penalty: abstraction obfuscation. By sitting above the execution engine, Keras loses granular memory control. If a hardware mismatch or compiler failure occurs deep inside a PyTorch autograd pass, the error propagates upward through the Keras API as a convoluted, opaque stack trace that is difficult to diagnose. Advanced distributed training is also bottlenecked. The native Keras distribution API, which abstracts data and model sharding, is currently only fully optimized for the JAX backend. But the rewrite also provided an opportunity to fix a severe enterprise vulnerability: model serialization. Historically, Keras relied on the legacy .h5 storage format. This format carried arbitrary code execution risks. As documented in CVE 2024-3660, malicious actors could inject weaponized Python bytecode into unverified Lambda layers, which would execute with full system privileges when a victim loaded the model. To mitigate this, the Keras team engineered the mu.keras version 3 format. It utilizes a zip archive that strictly separates the model's structural logic in a sanitized JSON file from the numerical state stored in an isolated weights file. This structural partition prevents bytecode injection by design. Keras 3 forces engineers to surrender line-by-line low-level execution control, but in exchange, it delivers XLA compiler speedups and enterprise-grade serialization security. Keras is not a universal tool. For computer science researchers building new forms of automatic differentiation, or hardware engineers writing ultra-low latency code for embedded microcontrollers, the overhead of this abstraction layer is unacceptable. If an algorithm requires manipulating gradients inside unpredictable conditional loops that defy standard acyclic graphs, native PyTorch remains the superior option. But those academic edge cases do not reflect the reality of scaling artificial intelligence within massive, cross-functional global enterprise teams. In a corporate environment, Keras acts as a technological diplomat. It provides a standardized language that data analysts, junior developers, and senior systems architects can all read and deploy. It allows organizations to effortlessly piggyback on the multi-million-dollar R&D compiler investments of rival tech giants without triggering massive codebase rewrites. Keras is a financial hedging strategy against vendor lock-in. It transforms AI infrastructure into a highly liquid asset, allowing an enterprise to write their code once and instantly migrate millions of dollars in compute workloads to whichever backend engine currently offers the highest performance per dollar.